इसके बाद should I start? Good afternoon to one and all. I am Dr. Vishalli. I am working as an assistant professor at IIMT College of Science and Technology, Greater Noida. Today's topic is PN junction as a rectifier. So today we are going to discuss a very basic electronic circuit that is called as a rectifier circuit. So this presentation, first of all, a brief layout of the presentation. In this session, we are going to discuss about the rectifier. First of all, there is a introduction there is some basic introduction about the junction diode. Then there is power supply. Then we will learn what are the rectifier circuit and what are their types. Basically, two types are there: half wave and full wave rectifiers. And lastly, we will compare the various rectifier circuit. So starting from its introduction, basically we are using a diode. In rectifier circuit, the component which is used is called as a diode. So diode has a very important property, that is a unidirectional property. Under this property, diode conducts in the forward bias that the diode excuse me the diode conducts in the when it is forward bias, and it is cut off when it is reverse bias. Using this property, the diode can be used. The diode has found many application in different circuits. So in rectifier also, we use this unidirectional property of the diode. So first of all, I'll briefly explain what is this unidirectional property and what is this forward and reverse biasing. So in PN junction, that is made by joining the p-type and n-type semiconductors. Whenever we have this PN junction diode, if P is connected to the positive and N is connected to the negative, then this PN junction is said to be in the forward bias situation. So in the forward bias, these are the forward characteristics which are shown in the figure in this figure. So in the forward characteristics, we are basically plotting the voltage with the current. So it can be seen that initially the current rises very slowly, but after some point, the current started to increase with the slight increase in the voltage. So we can say that after this point, the diode starts to conduct and the current starts to flow. So in the forward bias, we have seen from its characteristics that there is a current in the circuit in this forward biasing, and this current is due to the majority carriers which are present in the P and the N side. Whereas in the reverse biasing, the biasing is basically reverse, and P is connected to the negative and N is connected to the positive. So if we plot the reverse characteristics, taking voltage along the x and the current along the y axis, we can see that with the increase in the voltage, the current is increasing very slowly. After VB, which is called as a breakdown voltage, the current rises sharply. But before the breakdown voltage, with the increase in the applied voltage, there is a very small increase in the current. And the current which we are taking along the y-axis, the units of the current in reverse biasing, that is of the order of microamperes, whereas in forward bias, the current is in the milliamperes. So in the reverse bias, before VB, we can say that there is a negligible amount of the current which flows in the reverse biasing. The reason for this is that in reverse biasing, the current is due to the minority carriers, and there is a very small increase in the current with the increase in the voltage. So using these two properties, we can say that if we talk in terms of, say, ideal diode, then we can say that in forward bias the diode is conducting, whereas in the reverse bias the diode is cut off. A negligible amount of current is flowing, so we can say that it is not conducting. So in the and this also forms the basis of the rectifier circuit. It's a basic principle of the rectifier, that the diode, we are assuming that it is conducting in the forward bias and it is cut off or it is non-conducting in the reverse bias. So due to these property, due to this unidirectional property of the diode has found many application. One is a rectifier. It can also be used as a switch in the logic circuit, The switch is in the on position when it is in forward bias, and the switch is in the off position when it is reverse bias. And the other properties are, it is diodes are also used in clippers and clamper circuits, and one special kind of diode which is called as a Zener diode, it is used in the voltage regulation. So today we are going to discuss the rectifier circuit, and the property which is the diodes property which is being used in the rectifier is a unidirectional property. Next is a power supply. Now, what is the need of the rectifier circuit? So, mainly all the electronic equipments these days, they require the DC supply. But when we get from the mains, we are getting the AC supply. So we need to convert that AC to DC. So this nowadays, this power supply circuit is almost there in every electronic equipment, and the main purpose of this power supply circuit is to convert the AC into DC. So this is a block diagram of the power supply circuit, and a rectifier is is a part of this power supply circuit. So what is there in this diagram? First of all, we are providing the AC as an input to the transformer. Transformer helps in steps up or steps down the voltage according to the requirement of the DC which is required in the circuit. Secondly, that input is given to the rectifier circuit. The function of the rectifier is to convert AC into DC. Now the output which we obtain from the rectifier, it is not a pure DC. It also contains some portion of the AC as well as DC. So to remove the AC component from the rectifier output, the filter circuit is there, and after the filter circuit there is a regulator. The function of the regulator is to provide a constant DC output at the other end. It provides a constant DC output irrespective of the change in the load or the input voltage. If there is some change in the load resistance, or from here we are changing some input voltage, so the work of the regulator is to maintain a constant DC voltage across the output. So among all these, we are going to discuss this rectifier circuit. So up to now, we have discussed the rectifier circuit. The main aim of the main purpose of the rectifier circuit is to convert AC into DC. So for that purpose, in the rectifier circuits, more than one or two or four diodes are used. So rectifier circuits can be categorized into two types. One is a half wave rectifier, and second is a full wave rectifier. The full wave rectifiers are further categorized into two types. One is a center tap full wave rectifier, and another is a bridge rectifier. So we will start from the very basic, that is a half wave rectifier. So this is a half wave rectifier. This is a circuit of the half wave rectifier. So here we have the AC input. So from AC main we are getting this input, and this is a and the next portion is a transformer with the number of turns of N1 as a primary and N2 in the secondary coil. So the function of the transformer is to step up or step down the AC voltage according to the requirement of the DC. What amount of DC we require, according to that the transformer steps up or step down the AC input voltage. And the second purpose of the transformer, it also isolates this rectifier circuit from the AC mains. So in this way, it can also avoid the shock situation. So its main purpose is to step up or step down the voltage, as well as to isolate the rectifier circuit from the AC mains. After that, we are getting we have in this circuit the PN junction diode. There is a load resistance across which the output voltage is obtained. So in the half wave rectifier circuit, we are using only a single diode. So this VI voltage, it is an input voltage which is obtained across the secondary of the transformer. This is VM sine omega because this with the sine function, and this Vm is a maximum amplitude of this voltage. This is a maximum voltage of the AC. So this is the waveforms which we are represented in the first diagram. We are representing the AC mains. So in the AC mains, it is the maximum amplitude is Vm, and it is represented by a sine curve. Now whenever we get a AC around this, so this AC, if we consider it's one cycle, So in this one cycle, that is from 0 to 2 pi, we have two polarities. From 0 to pi, we can say that the signal is in the positive half cycle, and from pi to 2 pi, it is in the negative half cycle. So whenever so we will discuss it on the basis of the polarity. First, we will discuss it for the positive half cycle, then we will discuss it for the negative half cycle. So during the positive half cycle, the polarity is shown in the first diagram. The upper end become positive and lower end is negative. And if we see by this, the diode is forward biased, because now P is connected to positive and N is connected to negative. So whenever the diode is in the forward bias position, then according to the property of the diode, this diode will start to conduct. So whenever it is conducting, the current IL start to flow through this diode. So there is a voltage drop across the diode, which is 0.7 if the diode is of silicon, if and it is 0.3 if the diode is of germanium. But we will assume here that there is a negligible voltage drop across the diode, so that the input voltage which we are applying in is obtained at the output end. So during the positive half cycle, that is from 0 to pi, we are getting the output, the lower curves, the lower sine curve, it is representing the output waveform of the half wave rectifier. So from 0 to pi, we are applying the input, and the diode is in the forward bias situation. So we are getting the current in the circuit, and hence we are getting the output voltage. So from 0 to pi, this output voltage is shown. So in the next negative half cycle, that is from pi to 2 pi, if we see, now the upper end it becomes negative and the lower is become positive, meaning the polarities are now reversed, the polarities are now changed. So by the change in the polarities, we can see P is connected to negative and N is to positive. So that in this situation, in this polarity, this diode will become the reverse bias. So, and according to the property of diode, we assume that in the reverse bias, negligible current flows, or we can say that in the reverse bias situation, in the reverse biasing, the diode will be in the cutoff position and it will not conduct. So there will be no current in the circuit. If there will be no current in the circuit, no current is passing through the load, and we are getting the zero output voltage. So it is shown in this waveform. In the output waveform from pi to 2 pi, we are not getting any of the output. So if we talk about one full cycle consisting of one positive and one negative half cycle, we are getting output only in the positive half cycle and not in the negative half cycle. And whenever and again the circle, this cycle starts from 2 pi to 4 pi. From 2 pi to 3 pi, we are getting the output, but between 3 pi to 4 pi, due to the factor that this is a negative half cycle, we are not getting any output. So this is a net output which we will obtain in the case of the half wave rectifier. So half wave is able to rectify only half portion of the input waveform. So because in the second half, because it is not conducting due to its reverse bias situation. So this is the problem with this half wave rectifier, that it is only able to convert the one half into the output, and this output, we can say that it is a unidirectional output, but still it is containing the AC component. It has removed the negative half cycle, it is a unidirectional, but so we can say this is a DC, but it contains a AC component as well. So these are the drawbacks of the half wave rectifier. So as we have seen in the output curve, that we are getting a unidirectional current, but still there is a AC component present in the output. So we define this AC component as a ripple factor. So what is a ripple factor? It tells us about the amount of AC which is present in the output, right? Because in the output we are getting AC plus DC. It tells us about how much amount of the AC is present in the output. So greater is the value of the ripple factor, then more inefficient will be that rectifier circuit. So in the half wave rectifier, the value, if we calculate the value of the ripple factor, or we can say the value of the AC component, it comes out to be 1.21. It is greater than 1, which is quite high. So So that's why we can say that half wave rectifier is not a very efficient kind of rectifier circuit to convert the AC to DC, because we are not getting much of the DC, we are getting mainly the AC component. And secondly, due to this reason also, the rectification efficiency is merely 40%, and this value is the maximum theoretical rectification efficiency. In practice, the efficiency will be lower than the 40%. So which is also not a very good thing in the case of the, in terms of converting AC to DC. Thirdly, the transformer which we use in the half wave rectifier, it is not fully utilized. We define a term called as a transformer utilization factor, and we can also calculate that value. But in the half wave rectifier circuit has been found that the transformer is also not fully utilized. And next point is that the DC which is flowing through the secondary windings of the transformer cause a DC saturation of the core of the transformer. So to minimize this saturation, the size of the transformer needs to be increased. So if we increase the size of the transformer, it will also increase the cost. So cost wise, it is cost wise also it is not very effective. So due to these reason, these some of reason, this half wave rectifier circuit is normally we do not use it as a power rectifier circuit. Next, we will move to a full wave rectifier circuit. As the name suggests, full wave, meaning this full wave rectifier, it utilizes both the half cycles. As we have seen previously in half wave rectifier, it was able to convert only half of the wave into the output, but in the full wave rectifier, it uses both the half cycles of the AC input, the positive as well as a negative half cycle into the output, so that a unidirectional current flows through the diode during the entire cycle of the input voltage. And this full wave rectifier, as I have told earlier, that it has been categorized into two types. One is the center tap full wave rectifier and another is a bridge rectifier. So what happens, what is there in the center tap full wave rectifier? The circuit is, the transformer is same, we are applying the AC input through the transformer to the rectifier circuit. So in this rectifier circuit, we are using the two diodes. We are using two diodes, and this is RL in between these two diodes, across which the output voltage is obtained. And secondly, the main point is that in the secondary winding, we are using a center tap arrangement. So what is this center tap arrangement? In this arrangement, this center at this point, which is at the center of the secondary winding, we are keeping this point as a point in which the voltage, the reference voltage is zero, meaning the secondary windings, you can say that divided into two halves, right? So this, at this point, we will use this point as a zero reference voltage. For example, if we are applying V1 as a input voltage, and V2 is a voltage which is across the secondary windings, so due to this center tap, from the top of this secondary windings to this center tap, this voltage will get half, meaning Vi, the input voltage which is being fed to this diode D1, it is, or we can say that the input voltage which is for this upper half cycle, that will be half of the total voltage, that is V2 by 2. And similarly with the lower circuit, that is the input voltage is getting half. So V2 is being divided into two parts because of this center tap arrangement, and this is a load resistance across which the output is being obtained. So this is the circuit of the center tap full wave rectifier. Now you'll see it's working to understand how it converts the AC to the DC in both the half cycles. So if we talk about the positive half cycle, so this first AC input voltage, we have AC input voltage like this. This is sinusoidal wave, and it has a two half cycle. One is the positive half cycle and another is the negative half cycle. So first we will talk about this portion, only the positive half cycle, the first positive half cycle. During this positive half cycle, the upper end becomes positive and lower becomes negative. So it means that this diode D1, it is clear from this diagram also, this diode D1, it is P is connected to positive And automatically, if this is positive and the lower end is negative, so center tap, at the center tap the polarities will also be defined. So D1 is now forward bias because this P is connected to the positive, and we can say this N is connected to the negative. So D1 is forward bias now, so it means that it will conduct, whereas this diode D2, in this P is connected to negative and N is connected to positive. We can understand it like this. So D2 will become reverse bias and D1 will become forward bias. It means that D1 will conduct and D2 will not conduct. D2 will be in the cutoff situation. So whenever this D1 conduct, the current IL that will flow through this load resistance, and we will get the output voltage. And since there is no current in this lower circuit, so we are not getting any output voltage corresponding to this diode D2. So we can plot the output like this. Voltage across the D1, we are getting the result, but along the D2, we are not getting any of the output. So the net output will be represented in DC output voltage by this first curve, which is due to the voltage across the diode D1. So because D1 is in the forward bias in this situation. Now for the next half cycle, that is from in the next negative half cycle, when the polarity reverse, now the upper end becomes negative and the lower will become positive. Due to this diode D1 will now be reverse bias and the diode D2 will now be forward bias. Due to that, the current will flow in the lower circuit, but there will be no current in the upper circuit, and still we are getting the output voltage. So we can see whether it is a positive half cycle or it is a negative half cycle, there is a flow of the current through the load resistance and we are getting the output voltage. So it can be represented in waveforms like this. So in the final DC output, we are getting some output in both the half cycle, in the first as well as in the positive as well as in the negative half cycle. The thing is, during the positive half cycle, one diode become forward, another become reverse, and vice versa in the next negative half cycle. So output voltage will always be there in the output. The voltage will always be there. So this is the curve or waveform which by which we represent the output in the center tap full wave rectifier. So it can be seen clearly that both the half cycles are able to convert into the output. So in this case, this current is unidirectional again, but it also contains some AC component which is further removed by the filter circuit. So up to now, if we talk only about the rectifier circuit, this is the output which we are obtaining in the case of the center tap full wave rectifier. Next, second category is the bridge rectifier. So in the full wave bridge rectifier, we are using the 4 diodes. So 4 diodes are connected across the secondary of the transformer, and these are in the shape, it's just like Wheatstone bridge, so that is why it is called as a bridge rectifier. So we have the 4 diodes on the bridge rectifier. In the same way, we are applying the AC input to the primary of the transformer. We are getting the input from the secondary of the transformer. In this arrangement, no center tap is needed. So let us try to understand now the working of this bridge rectifier. You can see we have 4 diodes which are placed like as shown in this diagram, and this RL is a load resistance across which the output voltage is being obtained. So let's see what happens during the positive half cycle. During the positive half cycle, meaning when between 0 to pi. So from 0 to pi, this A will become negative and B is A is positive. Let us assume A is positive during the first half cycle and B is negative. So in this situation, if we assume A is positive and B is negative, then we can say this diode D2 and D3, they are forward bias because now P is connected to the positive and and the N is connected to the negative. And this diode D1 and D4, they will become the reverse bias, right? So in this way, 2 diodes will be forward bias and 2 diodes will be reverse bias. So at a time, for a particular half cycle, 2 diodes will be working and 2 will be non-conducting. So the diode D2 and D3, they will be conducting, and there is a resistance RL which is in series with these two resistance. We can say it is forming a Z type shape here, because we can discard D1 and D4 because they are in the reverse bias situation. I'm assuming that these are ideal diode and they are not conducting. So the circuit is from A to D, D to C, and then C to B, and then it completes the circuit to A. So this Z type circuit is formed here. So in this circuit, the direction of the conventional current is from P to N. So these solid arrows which are drawn here, they are representing the flow of the current. So in this way, the current is flowing through the diode and we are getting the output because this current is flowing through the resistance load resistance RL, and we will be getting the output voltage. So during the positive half cycle, if we see in the input and the output waveform from 0 to pi, since the diodes D2 and D3 are forward bias, so we will be getting the output voltage from 0 to pi. Now we will move to the next half cycle. The next half cycle is from pi to 2 pi. So from this negative in this negative half cycle, the polarities will get reversed. A will become negative, say, and B will become positive. So in this situation, diode D1 and D4, they will be forward bias, and diode D2 and D3, they will be reverse bias. So the situation will now be get reversed. So D1 and D2, they will D1 and D4, they will be conducting, and D2 and D3, they will be non-conducting. They will be in the cutoff state because of the reverse biasing. So here also the current is shown by these dotted arrows. So the current is flowing in this from P to N. These are shown by this dotted arrow, and also these two diodes are in series with this load resistance. So again, we will there will be the flow of the current in the circuit. There will be the flow of the current through the load resistance, and we will be getting some output voltage across the load resistance. So from pi to 2 pi, if we see in the output and input waveform, we are getting some output. So there is a output in both the half cycle, that is in positive and in negative half cycle. One important factor here also is that during both the half cycle, if we see when the diode D2 and D3 were conducting in the first half cycle, the direction of the current was from D to C, right? And whenever we move to the next half cycle, that is when diode D1 and D4 are working, the current is still across the load, the current direction is not changed, it is still from D to C. So it means that across the load we will be getting the output voltage, and the direction of current is also not changed. Same thing also happened in the center tap full wave rectifier, because if we see here also, the direction of the current is from right to left. Here also the direction of the current is from right to left. So across the load, the direction of the current is same. The two currents which are flowing in the two half cycle, they are not opposing each other. So the direction of the current in the case of the half wave and the in the case of the bridge rectifier and center tap rectifier, across the resistance, that is same. So we will be getting the output voltage. So this is the output waveform which is represented. Vm is the maximum amplitude of that voltage. So this is the output waveform which we obtained in the case of the full wave bridge rectifier. Also, this output, it will contain ripple because it has AC component, it can be clearly seen, but this is a unidirectional flow. And after the rectifier circuit, this output is being fed to the filter circuit. The filter circuit basically remove this waviness. This output is called as a pulsating DC, because it is DC but it is in the form of the pulses. So that is why it is called as a pulsating DC. So that was all about your rectifier circuit. Now we will compare the different. We have studied basically three rectifier circuit: half wave, and in full wave we have center tap and bridge rectifier circuit. So if we compare the rectifier circuit, half wave, we have already discussed that in the half wave, the efficiency of the rectifier is very less and the ripple factor is very large. So if we compare the full wave rectifier, whether it is center or bridge, we can say that there is much improved in the efficiency as well as in the ripple factor, right? Efficiency is being increased from 40 to 80%. This is the maximum value of the efficiency, and ripple factor is reduced. Ripple factor, in other words, I have told earlier that it is said to be the AC component which is present. So in the half wave rectifier, the AC component which present was 1.21, but in this case it is being reduced to 0.482. So this is the value of the ripple factor. So it means it is, and it is less, it is smaller than 1. So clearly the DC component is increased as compared to the AC component in the case of the full wave rectifier. And if we talk about the root mean square current and the DC current, so these values can also be calculated. The RMS current, root mean square current in the uh, half wave rectifier is Im by 2, and in the DC current is Im divided by pi. If we see in the full wave rectifier, the DC current has increased twice. The factor of 2 is being added, is being multiplied, so it has become doubled from the DC current in the case of the half wave rectifier. So from this we can say that the full wave rectifier circuit, they are the more practical rectifier circuit, because we can't use half wave rectifier because of its inefficiency and large value of the ripple factor. Also from center tap and bridge rectifier, we mostly in the circuit we use the bridge rectifier is better because it doesn't require a center tap. And one drawback of the bridge rectifier is that it contains 4 diodes. It becomes very bulky, and whenever we required a low DC output, that is not possible to get in the case of the bridge rectifier. If we want to get a low DC output, then we have to use this center tap arrangement. So but in other forms, if we say that bridge rectifier is better than this center tap arrangement. So that was all about the rectifier circuit. These are some reference books which can be used for the further studies. Thank you.